Okay, this is question 4 from the 2019 AS Physics paper from AQA. Again, this is to help with revision from a mock that we did. So, here we've got to set up John Tyndall sent a beam of light along a stream of water. So we've got a column of water with a laser beam going through it and a stream coming out of it. I'm pretty sure I did this demo. I love doing this demo. I think it's just so cool to be able to pour light like this. So the question is saying explain why the laser beam stays in the stream of water. So, well, what we're going to first say is that the N of the air is less than the N of water. So the refractive index of water is quite a bit higher than that of air, 1.33 versus 1 for air. Okay, this means that total internal reflection is possible. And here we have our angle of incidence is greater than the critical angle, so we get total internal reflection. So really, you've got to link in the fact that because this critical angle exists, because we're bending away from the normal, we will reach a point where our angle of refraction is 90 degrees, and it can't get any bigger than that, so we get total internal reflection occurring. And in that case, the laser beam will stay inside the stream of water. And if you had seen me do the demo, you would see that actually at a certain point, when the column of water is low enough, the stream is bending too much and the laser will actually escape. So we lose total internal reflection at some point. So calculate the speed of the laser light in water. Give your answer to the appropriate number of significant figures. So let's take a look at my physics data sheet. I'm pretty sure it uses 3.00 times 10 to the 8 for the speed of light. Yep. So you have to remember the definition of a refractive index. N is equal to speed of light in the medium. Nope, other way around. It's always a number bigger than 1. C, it's the speed of light in vacuole versus the speed of light in the medium. Okay, so the medium is equal to C divided by N, so 3.00 times 10 to the 8 divided by 1.33. Uh, 2.26 times 10 to the 8. Okay, so again, this is one of the questions where they were like, ooh, significant figures, significant figures. Our formula sheet gives us 3 sig figs. Our N is given to us in 3 sig figs. Your answer must be in 3 sig figs, or you will only get 2 marks, assuming you've done the math correctly. Okay. So, critical angle. So, sine theta c is equal to N2 over N1. 48.8 degrees. So 48.8 degrees. Okay, so all of it is very straightforward applications of math so far. As long as you know the formulas and know what the symbols mean, then you'll be okay. Okay, so step index optical fiber. Okay, so I'm going to just point form this, but this is what you would have to talk about. So X and Y, you'd start by naming them. X is the core, and Y is the cladding. Okay, so X, and then what does it do? Well, X carries or propagates the light. Okay, basically make sure it goes where it's going. And it uses the idea of total internal reflection. Okay, and Y, it is protective. So it covers the core, prevents it from damage. It prevents crosstalk if you've got a bundle. So for example, the cables that carry the internet, the fiber optic cables that carry the internet, there'll be a very large bundle of wires, and you'll have a core and cladding, and then those will be wrapped up to make the bundle. So it prevents one cable from accidentally interfering with another cable, and it's to ensure or it ensures that we have a low theta c. So in other words, it will have a low index of refraction. Okay, so it's to provide a nice boundary so that stuff can bounce off. Okay, now here we go. Modal dispersion versus material dispersion. So modal dispersion essentially what happens is that you can have that if you have a ray that travels directly down the center of the core versus one that has bounced several times. Bounced, what a terrible, terrible word. Never use the word bounce when we're talking about reflections in physics. So if it reflects multiple times, the path will be much larger. So diagram that out. Okay, so you've got ray number one, which goes straight through. So its distance that it travels is much less than a ray that travels like that. Okay, and the way that we minimize that is by having a small radius. Okay, so make sure that X is as thin as possible. Okay, the other thing is that you want to have as short a cable as possible. Obviously, for long distance travel, what you'll probably end up doing is a software solution at the end that will compensate for that dispersion. So it'll be a relatively known amount, and you can use software for it. But in the design of a cable, we want it to either make sure that we have a really, really short cable, which is not always that useful, or we have a really, really, really thin cable, which has its own problems. You can't transmit as much information in a thin cable as you can with a thick cable. It's just the way that it is. But it's a trade-off. So the last one, material dispersion. Okay, this is because white light will disperse. In other words, it will end up as a rainbow. Okay, just like a prism, and that's because n is frequency dependent. And if I remember correctly, you would have sort of red light will move more slowly through a given substance compared to violet light. So that's where you'll get this material dispersion. So the solution is to use monochromatic light. And most fiber optic systems will use towards the red end of the spectrum. So if you use monochromatic light, this will not be a problem. Oh, and I was backwards. It looks like it's violet light that is more slow than red light when it comes to moving through glass. But either way, it's the same effect. The different frequencies travel at different speeds. So you get this white light dispersing, and again, you could do a software solution if you really wanted to, if you're thinking with a sort of an electronics mindset, if you really want to have white light, like that's the only thing that you have that you can use. You could do a software thing at the end of it. But the other option is to have a short cable because there's not enough time for the light pulses to separate out. But in general, what we'll do is we just use monochromatic light. Okay, so put all that information together into a nice, readable paragraph, good grammar. Remember, organize your thoughts for these kind of questions. But that's the content that we would be looking for. Okay, so here, let me draw my diagram. It says draw your diagram. So look, this light goes through here, and it will reflect. Okay, so suggest why the amount of reflected changes. So it is possible that of impurities it will change. Okay, sorry about that. My microphone cut out because apparently if there's no sound coming through the headphones, even though the microphone is in use, they shut off. Okay, so the number of impurities hit will change. Okay. Okay, so when bent, you will have more light as the path taken is different. Okay, so that's the kind of idea that we have to be looking for. Okay. We can also talk about how it's possible that the critical angle, like fewer beams of light will be at the critical. So if it bends a lot, you'll have less at the critical angle. But you have to talk about this change, okay? And that the path that it's taking is different. So we will have a different amount of light that gets absorbed and makes it through to the end. Okay, and again, this is a very easy, straight up. You've got to just know it. You have to know the definition. The A-level definition of transverse and longitudinal waves. So I would always define it like this. Okay. For transverse waves, the direction of oscillation is perpendicular to the direction of propagation. Okay, so I would almost always use those words. You could also say, instead of propagation, the direction of the direction of energy transfer. Okay, because that's what propagation means. Okay, and longitudinal. Okay, your oscillation is parallel to the direction of propagation. Okay, the mark scheme specifically says direction of energy transfer, but if you propagation is the direction of energy transfer, so you should still get the marks. It should be all right. So that is question number 4.